especially at this time. This is probably the most important kinds of things to be thinking about for the rest of the semester, actually. This kind of thought process about factor rings and these kinds of computations with modular arithmetic and factor rings is going to come up over and over again through pretty much the whole rest of the semester. Look at this thing first here. Re-emphasize some things. So again, we're talking about this particular factor ring, where the original ring we were modeling by is Z2x, polynomials with coefficients into Z2. A is the principal ideal generated by x squared plus 1. I said that this meant ultimately that since x squared plus 1 is in A, that x squared plus A equals negative 1 plus A, but negative 1 is 1 in Z2, and so x squared plus A equals 1 plus A. Let's confirm by hand that this is a zero divisor. And we saw, in fact, on Mathematica that when you square it, you get 0. Let's confirm that by hand. By the definition of coset multiplication, when you multiply two cosets, you multiply their representatives. And that's a well-defined operation when A is an ideal. That's the motivation for the definition of an ideal being superabsorbent, because if A were just a subring that's not an ideal, it turns out the multiplication is not well defined. This would be x plus 1 squared plus A. You multiply the coset representatives. Just keep the plus A there. In case you were ever wondering, you might want, why don't I have an A squared or something like that? Well, A is the ideal. It's got to stay as is. It's just notation. It's the representatives that get multiplied. You multiply that out without modding, you could write it like that. But of course, we then mod by mod 2, that's 0. But then x squared can be replaced by 1. And then 1 plus 1 is 2, mod 2 is 0. This is the 0 element of this factor ring. Yeah, ideal itself, so to speak, is 0 plus the ideal is the 0 element of the factor ring. Yeah, additive identity. That confirms it's a 0 divisor, so again, this factor ring cannot be a field. Fields don't have any 0 divisors, they are integral domains. Coming back up here to the other one, in Z3x mod A, x squared plus 1 is still an A, and that means x squared plus A equals negative 1 plus A, but now we're doing mod 3 arithmetic, so negative 1 is the same as 2. The additive inverse of 1 is 2 in Z3. It's mod 3. And so, for example, we could do a calculation in that ring. We could try, well, let's try to confirm something in the multiplication table there. Here was the multiplication table. This is the addition table, by the way, right there. That's the addition table, which is a Cayley table. Technically speaking, the multiplication table is still not a Cayley table because we got all the zeros in there. If we took away the zeros, then it would be a Cayley table for the group of units, which would be all the non-zero elements, because it is a field. We might wonder, what is the multiplicative inverse of, say, 1 plus 2x? Well, according to the Cayley table, it's, can't quite see it. Two plus 2x, 1 plus 2x plus A times 2 plus 2x plus A gives you 1 plus A. Again, you don't see plus A's in there because that's not something Mathematica knows about, and it would be kind of a pain to put it in there. Not necessary. We're working with coset representatives. Let's confirm that by hand. 1 plus 2x plus A. I guess I'm now writing like Mathematica does from lowest degree to highest degree. It doesn't matter. This should give us the multiplicative identity. It should give us 1 plus A. Not 0 plus A, because then these would be 0 divisors if that were the case. go ahead and multiply the coset representatives. That is the factor ring multiplication operation. Foil it out to get 2x plus, oops, mistake, sorry. 2 plus 2x plus 4x plus 4x squared plus a mod 3. This can be simplified to 2 plus x squared plus a. Right? Mod 3. 6x is 0. 4x squared is x squared. But now replace x squared with 2 because of this. This is 2 plus a, which mod 3 is 1 plus a. The multiplicative identity. This verifies that the multiplicative inverse of 1 plus 2 plus x plus a is 2 plus 2x plus a. Just like Mathematica showed by having the 1 right there. I think it's pretty cool Mathematica code. Again, I didn't have to create this PM function. I could have just used polynomial mod itself. It just made the code down further easier to read by doing that. But here is code that creates the addition table, which is a Cayley table for the group under addition. This creates the multiplication table, which is technically not a Cayley table, because again, technically the entire field is not a group under multiplication, but if you take away 0, it is. So, but I included 0 in the table anyway. I guess you want to pause that and write that down or something. Well, if you're watching the video. Otherwise, again, it's going to be in the Google Drive. These are the most important kinds of calculations. And there are going to be some other related calculations. We will still be doing long division and synthetic division. Those kind of calculations really, really help you understand the theory because they illustrate the theory. They're not proofs, but they illustrate the theory. The theory becomes very abstract as you're experiencing. It's good to make it concrete with examples. And the examples themselves are actually have theoretical importance too, as we will see when we get to chapters 20, 21, and 22. The examples themselves have theoretical importance. All right, for the remaining time, let's talk about chapter 15. Ring homomorphisms. Oh, and by the way, we were illustrating these two facts here essentially as well in the calculations. Not proving them, but illustrating them. The ideal is maximal if and only if the polynomial is irreducible over the field. Over Z3, x squared plus 1 was irreducible. Over Z2, it wasn't. Yeah, if it's irreducible, then this is going to be a field. Actually, this corollary could have been an if and only if. If this is a field, then P of x would be irreducible as well. Over F. All right, ring homomorphisms and isomorphisms. So that's chapter 15, which we've not talked about yet. So we're talking about it now in 20 minutes or so. And this is what your completion problems to work on for Monday are on. You don't have to turn them in, just do as many as you can. Let R and S be rings. What is a ring homomorphism? It's operation preserving mapping from R to S. But remember, there's two operations. So I call this doubly operation preserving. It's a mapping from R to S. It's a ring homomorphism if it's doubly operation preserving. If it preserves both addition and multiplication. Phi of A plus B equals phi of A plus phi of B. And phi of A times B equals phi of A times phi of B for all A and B in R. As with group homomorphisms, you should make sure you realize where these operations are being done. this plus here, for example, is an R, but this plus there is an S. This multiplication is an R, this multiplication is an S. If the ring homomorphism is 1-to-1, also called conjecture, if it's both 1-to-1 and onto, injective and surjective, it's called a ring isomorphism. When a function like this is 1-to-1 and onto, we also call it bijective. That's just a reminder. Okay. Go to grad school, you'll definitely hear those words. Grad school in math, at least. Injective, surjective, and bijective. So it's nice to hear those things. Then again, it's a ring isomorphism. And as the text emphasizes, isomorphisms and homomorphisms are both important, and they both kind of have different roles. Isomorphisms help you identify rings that a given ring is the same as, that maybe you're more familiar with. Homomorphisms help you sort of simplify rings, just like they do with groups, because if your homomorphism is not 1-to-1, it'll sort of map onto a quote-unquote smaller ring that might be easier to understand. Simpler ring. As a review of commutative diagrams, it's good to see that the operation preservation can be conceptualized in a commutative diagram. I thought it would be nice to quickly review the idea of a commutative diagram here. The book gives you another visual for this situation that's not a commutative diagram in figure 15.1, page 264. But just to remind you, just for the purpose of reminding you what a commutative diagram is, I thought I'd illustrate it. It's kind of a nice way to conceptualize it, to visualize it. Let's consider the multiplication. Well, let's consider the addition, actually. Remember, both addition and multiplication are binary operations. So they are really functions on a domain that is the set of ordered pairs of the ring elements, in this case, the Cartesian product. Writing an X there instead of an O plus. We need this as just being a set. Addition, for example, is a binary operation. It's going to take an arbitrary element here and give you a ring element. And the fact that it's closed means the codomain is R itself. Phi is a ring homomorphism from R to S. I could maybe write something like that. I also have an addition in S that I could also think of as being a binary operation, as a mapping from S to itself. I could write a plus sign there as well. Technically, this is the addition in R. Maybe write something like that. Technically, this is the addition in S. Maybe write something like that. It's not a full commutative diagram yet because I haven't closed the loop. What mapping should I put from here to here? Well, it actually makes sense to call it phi cross phi. What is phi cross phi? Phi cross phi is what you would guess it would be if you had to guess. Takes an ordered pair in R cross R and maps it to the corresponding ordered pair phi of R1, phi of R2 in S cross S. I claim this diagram commutes, which means people sometimes put these little lines in there to emphasize it commutes. And what does that mean? It means you can start over here and get down to here in either direction and you get the same thing. And that is the essence of operation preserving with respect to addition in this context. Why? Well, let's do it across the top first and then across the right. Remember, with function composition, you work from right to left. Well, let me use A and B here. Plus of AB, kind of weird notation. What does it mean? It just means add A and B, that's all it means. That's a function composition. Add first, then apply phi. I should get the same thing if I go around the other direction in the diagram. If I apply phi cross phi first, and then add. But what is phi cross phi of AB? It's that ordered pair. I'm going to add the elements in the ordered pair, phi of A comma phi of B. That means I add them. I write it like this. And if it's a ring homomorphism, these are the same. That's a way to visualize the operation preserving. I could make a similar diagram with multiplication as well. Being the binary operation. Okay. Some people find that kind of thing helpful. Some people find it confusing. Okay. Again, the book has another way of visualizing the doubly operation preserving property in terms of drawing sets as blobs. That kind of picture. I think they're both worth looking at and thinking about. Examples of ring homomorphisms. These are all examples you should try to remember to the best of your ability. I'm not going to prove facts here, just state these facts, but they should make some sense. They are kind of natural. Emphasis on the word natural. A natural ring homomorphism from Z to Zn always exists, no matter what n is. N is a positive integer. How do you define it? The natural way to do it is to map an arbitrary integer to that integer mod n. Divided by n, find the remainder. That's the most natural thing to do. We call it a natural homomorphism. And it is. It can be proved to be a ring homomorphism. Essentially, it's properties of modular arithmetic from chapter 0 that allow you to prove that's a ring homomorphism. Ring homomorphisms, just like group homomorphisms, have kernels. And just as kernels for groups were normal subgroups, so kernels for rings are ideals. And we can form the factor ring by kernels, and they end up, there's a first isomorphism theorem. That's pretty much the same statement, except you replace the word group by ring. What would the kernel of this mapping be? What elements, such that when you mod them by n, give you 0? Multiples of n. It would be the ideal generated by n. nz would be the kernel of this. There are many natural ring homomorphisms from this polynomial ring into R itself. You can write those natural homomorphisms this way, in terms of a formula. Given an arbitrary real number a, define phi sub a from the polynomials with coefficients in R to R itself by this formula. Take an arbitrary polynomial and plug in a. If a happens to be 0, by the way, that might be the most important one of these, when a is 0, then you're going to plug in, you're going to find f of 0, which is the same as the constant term in the polynomial. So that's a special case of this, perhaps the most important special case is when a is 0. But this works for an arbitrary a as well. You can verify this is operation preserving. It's pretty simple, actually. It's one of those things where it's almost so simple it's confusing. Think about it. Actually, I think one of the homework problems you end up thinking about this. Given two commutative rings, R and S, and a ring homomorphism from R to S, there is a natural homomorphism that is induced, called phi bar, from the polynomials with coefficients in R to the polynomials with coefficients in S. What do? You apply phi to all the coefficients. Phi bar applied to an arbitrary polynomial with coefficients in R is a new polynomial with the same degree, whose coefficients are coefficients in S. They are what the original coefficients get mapped to under phi. It's harder to prove this is a ring homomorphism. It's easy to prove it's operation preserving under addition. Multiplication, though, is a pain. Showing this is operation preserving under multiplication is so much of a pain that I don't really want to do it. I don't have time today anyway. But this is, if you think about it, this is kind of a natural thing to do. It's a natural. Induced means it comes from another homomorphism. That the original homomorphism sort of allows you to create this new homomorphism. There is an exercise where you are going to identify the possible ring homomorphisms from, for example, Z20 to Z30. That's one of your completion problems for Monday. I was going to go over it here, but I don't think we have time. I will give you a little hint about it here, though. You thought about a similar problem with group homomorphisms back in chapter 10. And the idea with group homomorphisms, and by the way, ring homomorphisms are group homomorphisms, because rings are groups under addition. So as far as addition goes, it's going to have all the properties that group homomorphisms do under addition. Back in chapter 10, the emphasis in such an example was to figure out what does 1 get mapped to, a generator of the cyclic group. That's the domain here, Z20. It gets mapped to an arbitrary A, call it. If you know what A is, then by operation preserving properties, you know what the rest of the homomorphism is. For example, phi of 2 would then be phi of 1 plus 1. Phi of 1 plus phi of 1 is A plus A, which we typically write as 2A. Once you know what it does in a generator, you know what it does to the other elements, and we can do this for the other elements. The order of A, group order, under addition, has to divide the order of 1, so it has to divide 20. For this example. And as an element of Z30, it also has to, its order has to divide 32, also. So then you have to ask, what are the possibilities? What are the numbers that divide both 20 and 30? What would they be? 1, 2, 5, 10. Is that it? 1, 2, 5, and 10? Those are the possible orders of A. Not the values of A, but the possible orders of A. Group orders under addition. So A could, for example, be 15 in Z30, because in Z30, 15 has order 2. But then you also have to think about the fact that it's a ring homomorphism, so that it preserves multiplication as well. And so that might possibly reduce further the possibilities for what A is. The book does an example. I got the key. You should make sure you think about that problem. Properties of ring homomorphisms. Again, all the properties of group homomorphisms carry over with respect to addition. So all those properties back in chapter 10 on group homomorphisms and in chapter 6 on group isomorphisms are going to carry over for ring homomorphisms and isomorphisms under addition. But again, you also have being operation preserving under multiplication, so there could be other things. In addition, images of subrings or subrings. You know what I mean by image? Set of all outputs. A subring under the homomorphism is going to be a subring of the codomain. Images of ideals are ideals when the homomorphism is onto, actually. It's got to be onto. Doesn't have to be 1-to-1. So it's got to be onto. Pre-images of ideals are ideals, and there's no restriction on it being onto there. Pre-image, everything in the domain that gets mapped into the given set. Use the phi inverse notation, even if phi inverse doesn't exist as a function, even if phi is not 1-to-1. The image of a unity, 1, under a non-trivial onto ring homomorphism is also a unity. You can prove that even if you didn't know the codomain had a unity to begin with. This would prove it has a unity. Kernels are ideals, yay. Can form factor rings by kernels. And ideals are also kernels. There's a first isomorphism theorem for rings, and its proof is practically the same as the one for groups, except you have to verify operation preserving under multiplication as well. A few more things to emphasize here quick. There is a natural homomorphism from Z to any ring with unity. And any ring with unity contains a subring either isomorphic to Zn or Z. The natural homomorphism from Z to any ring with unity is to take an arbitrary element of Z and, well, put it in front of the unity, meaning add the unity to itself n times if n is positive. That's the natural homomorphism from Z to a ring with unity. And it turns out that, again, any ring with unity contains a subring, either isomorphic to Zn or Z, depending on what the characteristic of the ring is. If the characteristic is 0, it's got a subring isomorphic to Z. If the characteristic is n, it's got a subring isomorphic to Zn. Interesting and possibly useful thing. That's it. Have a good day.